All right, in this third installment on velocity time graphs, we'll look at what we can find when we figure out the space between the graph line and our zero line. It actually does tell us something here. If you keep in mind that basically velocity is described as the change of position over change of time. If you are taking the velocity v and you multiply it by the time delta t, you're going to end up with the distance that you've traveled, because x, delta x, your change in position, is going to be velocity times time. So if we figure out the area between the graph line and 0, if we can calculate this area, then we can calculate the distance that we'll travel. Now it's going to be in units, in this case, of meters per second multiplied by second, so that'll give us our answer in meters. Now here are the three most common possibilities for velocity. The first one is if we have constant velocity, so the velocity is staying the same. Okay, so the velocity in this case, again, is staying the same. It's 6 meters per second. If we multiply that by the rectangle, we're talking base times height, we multiply that by the 6 seconds, then we get 36 meters of distance covered. Now, if the velocity is changing, most likely it will be changing at a constant rate, so that will give us some kind of sloped line. In that case, we form some kind of form a triangle, and the area of a triangle is just 1/2 of the rectangle, so it's 1/2 of base times height. So here it would be 1/2 of 6 times 6, which would be 18 meters. Now another common possibility is we're already in motion, we're moving, and then we increase our speed as we move. So in that case, we get multiple different shapes. No problem, we just have two different shapes in this case, a triangle and a rectangle. The key is this distance right here. We need to know 6 minus 2 equals 4 meters per second. So for a triangle, it will be 0.5 times 4 times 6 gives us 24, plus the 2 times 6 for the rectangle will give us 24 total. We just add all the areas together. If there are more than 2, again, we would just add whatever different shapes we had until we got to that final result. Okay, so examples of that down here. Here we have constant velocity. It's going to be, it's a rectangle, it's going to be base times height. So it's going to be 8 seconds times 12 meters every second that I travel. 8 times 12 is going to be 96 meters. In the next one, we're increasing our speed, so we're traveling further the more time goes on. Notice we didn't travel very far at first, but now we're traveling a lot of distance down here at the end. So again, that forms a triangle. So that's going to be 1/2 of the base of 8 times 12. And again, 1/2 of 8 times 12 is half of the 96. That's going to be 48 meters. And then this one, key spot here is the 4. So during the triangle part, we've gone from 12 to 4. So the height of that is 8. And then we're doing that for 8 seconds. So we have a 1/2 of 8 times 8. So half of 64 is 32. Plus, we're going to have to add to that the rectangle part. That's this section down here. That's 8 times 4, which is 32. So we have to add 32 to 32, and we end up with a total of 64 meters traveled. So just keep track of the different spots. Use highlighters if you need to mark out the areas. Nothing more complicated than a rectangle and a triangle, or a combination of those two for our types of motions that we're seeing. Okay. And finally, we're going to take a look and see, once we get fluid in the language, you should be able to put all of these different elements together. So here we're going to look at the position time graph and see how should that look for a velocity in a velocity time graph. So I look here for the position time graph, some key elements. it looks like my slope is 0 at the beginning. And again, the slope of position time graph is my speed. So I should start at 0. And then I'm getting faster. And I'm getting faster because the curve, the slope is increasing and it's getting more and more positive. So it's going to go more and more up. Now that shape of that curve is a parabola. So I should expect that the acceleration is constant, which means the slope is constant, which means in this case the velocity is going to constantly increase. So it should look something like that. Okay, positive slope, because the slope is acceleration, we're moving in the positive direction and we are speeding up. And now the next one, it's kind of the reverse. We're starting with a pretty steep slope and that slope is negative. So that means I'm going to need to start down here somewhere. Now I'm going to undergo acceleration, it looks like, for a while until I get to this point when I'm going to be essentially at a flat slope, and slope of position versus time is delta x over delta t. That's our velocity. So that means we're going to be stopped when I reach that point. Now it doesn't look like we're stopping our measurements, so for a little while we're going to be at 0 velocity. So here's a case where I'm going to be moving. I'm going to get to a point as I move along in the negative direction. I'm going to get slower and slower and slower, and then we're going to stay stationary. Now, the only place on a velocity time graph where you are stationary is 0. Common misconnect is that a flat line anywhere on a velocity time graph would be 0 speed, because that's what it was on a position time graph. This is 0 slope, that's 0 speed. The only place where we have 0 velocity is right there on the 0 origin of the axis. So that's the only 0 velocity spot. Okay, so that's some of what we can get from a velocity time graph. They are very handy because we can get position if we take the area, we can get the acceleration if we calculate the slope, and we can also get the velocity just by reading the graph. So of all the graphs for motion, velocity is the most useful. It can give us the most information. And that's it for velocity time graphs.